Hi everyone, today we are working on section 9.1 on sequences. So in a sequence in general, our domain is the set of natural numbers. So 1, 2, 3, 4, etc., etc. Occasionally, we will include a 0. In that case, our domain would be the set of whole numbers. Usually, though, natural numbers. Sometimes we use a mapping diagram. So first term goes to a sub 1. Second term is denoted as a sub 2. Third term denoted a sub 3. And our nth term denoted a sub n. And we go on from there. So this a sub n by itself is just denoting the general nth term. If we include braces around a sub n, this is denoting the entire sequence. So a quick example, sequence a sub n. For this first one will be -4 plus -1 quantity to the n. So in our first one, n is 1, -4 plus -1. That would be mapped then to a -5. Our second term, -1 quantity squared, flips it over to a +1. -4 plus 1 is -3. Third term, we're back to -1 to an odd power, stays -1. We're back to a -5. And notice it would just keep flipping back and forth like that. So just alternating -5, -3 forever. So that's one example of an infinite sequence. We'll try another one. We'll name this one b sub n. This will be n over 1 minus 5n. So here, when n is worth 1, we have 1 over 1 minus 5 times 1. So -1/4 for a first term. When n is 2, we have 2 over 1 minus 5 by 2. So we have 2 over -9, -2/9, and so on. 3 over 1 minus 5 by 3. So then we have 3 over 1 minus 15, 3 over -14. And so on. All right, so I'm going to have you all try one out. So c sub n is going to be n squared over 2 to the n plus 1. So take a minute and see if you can find the first 4 terms of that. So go ahead and pause the video and play it when you're done. Okay, welcome back. So when n is worth 1, we have 1 squared over 2 to the 1 plus 1. So our first term is 1/3. 2 squared over 2 squared plus 1. So we have 4 over 5 is our second term. 3 squared over 2 cubed plus 1. So 9/9 is just a 1. and 4 squared over 2 to the 4th plus 1, we have 16/17. And that would just go on forever. Yes, with the top here. Sometimes our infinite sequences are defined recursively. So since I'm not super creative naming stuff, we'll call this one d sub n. Defined recursively as d sub 1 is 4, d sub n plus 1 is d sub n plus 6. So basically what this says is that your first term is 4, and each subsequent term adds 6 to the previous. So d sub 2, so n is 1, 1 plus 1, 2. D sub 2 is d sub 1 plus 6, so 4 and 6, we get a 10 there. And then d sub 3, we take d sub 2 and we add 6. D sub 4, take d sub 3, add 6, and so on. So far, just sort of a little bit of pattern recognition. Next, we look at the idea of the limit of a sequence. So the limit as n goes to infinity, a sub n equals L. L is somewhere in the set of reals. If, hopefully you've seen the symbol before. If not, this is for all. If you see an upside down capital A in a math book, for all. So for all epsilon greater than 0, there exists. So capital E backwards, there exists m greater than 0 such that difference between our nth term and the limit is less than epsilon whenever n is greater than m. If the limit exists, the sequence is said to converge. All right, so let's translate this into English before we move on to the next page. So what they're saying is that the sequence starts approaching some limit, starts approaching one number as we start putting more and more terms into the sequence. This limit is some real number if for any epsilon greater than 0. So in other words, you tell me what close is. You tell me how close you want me to be. Do you want me to be within 1/10 of a unit away? Do you want me to be within 1/1,000,000th of a unit? Just some very small positive number, you pick it out. Once you've picked that out, I've got to be able to find a number m, also greater than 0, but m is sort of an index here that is definitely in our natural numbers, so obviously greater than 0. So there is some term, maybe it's the 50th term, maybe it's the 1,000,000th term, maybe it's the 2,000,000th term. There's some term that everything after that, the distance between my limit and the other number, they're less than your definition of close. So after the 200th term, all of my terms are less than 1/1000th away from the limit. Again, you picked out epsilon though. So for everything after that term, we're all inside of that basket. So if that happens, then our sequence converges. If it doesn't, then the sequence diverges. All right, so let's take a look at something from back in our algebra days that we took a look at and sort of used an early idea of limits with. Hopefully you recognize this as being something that goes to e. Limit as x goes to infinity, function f of x is e. So what this tells me is if this happens with the function, then this will also happen with the sequence. So therefore, if I have set of all a sub n, and I describe it as 1 plus 1 over n to the n, for that then I know that the limit as n goes to infinity a sub n would also be the same number, in this case e. So if we can set up a function that looks like it and we know the limit of that function, then the sequence also has that same limit. All right, so let's look at another one of these. A sub n. For this one will be -1 to the n plus 5. If I look at what this does, a sub 1 is a 4. -1 to the first is -1, -1 and 5 is 4. A sub 2, -1 quantity squared is 1, 1 and 5 is 6. A sub 3, though, I'm back at a 4. A sub 4, now we're back at a 6. This would keep flipping back and forth forever. It's not going to approach one single value. So on this one, the limit does not exist. So even though we're constantly just flipping between two values, we're not heading towards one value like we would be here. This one, bigger and bigger values of n, you're eventually going to start getting close to 2.718, etc., etc., etc. All right, another one of these, set a sub sequence a sub n. This will be 4n over 1 minus n. On this one, we can kind of think of what we did back in our function days. So we're looking for the limit as n goes to infinity of 4n over 1 minus n. Well, back in our function days, we could just multiply top and bottom by 1 over n. That's exactly what we can do with this limit in our sequence work. So multiply top and bottom by 1 over n. So now we have the limit as n goes to infinity of 4 over 1 over n minus 1. As n goes to infinity, 1 over n will go to 0. Numerator staying still, denominator getting bigger and bigger without bounds. 1/2, 1/3, 1/4, 1/100th, 1/1,000,000th. We're heading to 0 on this guy. So this one is heading to a -4. This limit does exist. So this is a series that converges. This one, the limit did not exist. This diverges. This other one, the limit did exist. This converges. Now our friend L'Hopital, his rule does still come up in this work. If we look at sequence b sub n, we have 90 n squared over 2 to the n plus 4. I want the limit as n goes to infinity. At the moment, this will turn into infinity up top. 90 times infinity squared is infinity. 2 to the infinity plus 4, also infinite. So since this has the infinity over infinity form, we can use L'Hopital's rule. So limit as n goes to infinity, differentiating the top, 180n, differentiating the bottom, natural log of 2 times 2 to the n. The plus 4, of course, drops. If I let n go to infinity, again, we still have infinity over infinity form, unfortunately. So we can apply L'Hopital's rule again. So now we have the limit as n approaches infinity of 180 over natural log of 2 squared times 2 to the n. At this stage, now my numerator is a constant. My denominator is growing without bounds. This one is approaching 0. So this one diverges. This one converges to 0. All right. Factorials. You may not have seen those in a little while. A quick little review on those. Just recall the definition. N factorial, n by n minus 1 by n minus 2, all the way down to n minus 3, 4, 5, 6, etc. until you hit a 1. So we stop when we hit a 1. N has to be in the set of natural numbers. Well, technically we could expand it to the whole number since 0 factorial is defined to be 1. So even though that one doesn't fit the pattern that works on the rest of them, that does help a lot of our formulas work in probability and statistics. So 0 factorial by agreement is defined to be 1. So those are going to come up. We also will be playing around with the squeeze theorem. So the idea here, if the limit as n goes to infinity of a sub n equals L, and that's the limit as n goes to infinity of b sub n, and there exists an n in the set of natural numbers such that a sub n is less than or equal to c sub n, less than or equal to b sub n for all n in n, then the limit as n goes to infinity of c sub n is equal to L. In other words, if we can't find the limit, but we know that the limit below it and the limit above it have the same value, if it's bounded above and below by 5, we know it must be a 5. So the idea here is we have some function above, some function below. It's bouncing around, but eventually these are both heading to the same value. Then our function has to be in between. It must be that same value. It has to share that same limit. All right, so let's play around with another one. C sub n is going to be negative 1 to the n times 43 over n factorial. So here we're going to compare n factorial with another expression 2 to the n at n at least 4. So n factorial, 1 times 2 times 3 times 4. So we know n's at least 4. So here's at n equals 4. Then we have times 5 times 6 times 7 times 8 times etc. times n. Two to the n, 2 times 2 times 2 times 2. There's our first 4. And then times another 2, times another 2, times another 2, times another 2, times times another 2. So n factorial, 24 times 5 times 6 times 7 times 8 times times n, 2 to the n. Grab those first group together, 16 times now a whole bunch of other 2's. So for n at least 4, we can see that n factorial is going to outpace 2 to the n. So we can say negative 43 over 2 to the n is less than or equal to negative 1 over n, 43 over n factorial, which is less than or equal to 43 over 2 to the n. Okay, so negative 43 over some big number, that's going to drop close to 0. And the limit as n goes to infinity of 43 over 2 to the n is also 0. And we know that this is in between them. So it's bounded below by 0 and it's bounded above by 0. Therefore, we know that this limit is 0.